So this is the type of question we want to use these manipulations on, because we can't manipulate sine x and cos x any other way, because if it was equal to 0, it's not a problem. We can shift cos across, divide by cos and get a tan, and we're in play. But with 1 there, we can't do anything about it. So we must manipulate sine x plus cos x into some form, and I'm going to do it to r sine x plus alpha. And so from that situation, r would be root 2 like we've done before. Tan of alpha is 1, so alpha's pi on 4. So we can write sine of x plus cos x as root 2 sine of x plus pi on 4, which means that when I go to solve this equation, sine x plus cos x equal 1, I can write it like that. I can't solve that with the 1 there, but I can start to solve this, because it goes back to one of those equations we had before. It was root 2, I can divide by that, and that gives me sine of x plus pi on 4 on 1 on root 2. Now, I'm going to consider the three values here because of the idea that x is between 0 and 2 pi, but when I add pi on 4 to the x, then my domain becomes between pi on 4 and 9 pi on 4, which means that when I do inverse sine of 1 on root 2, they'll give me pi on 4 and 9 pi on 4, because that's in my new domain here. Because if I subtract it, that's going to give me back to 0. That gives me back to pi on 2, and that one gives me back to 2 pi, which is x is between 0 and 2 pi. The trick here with, like, a lot of times is people would forget about that solution. So be really careful that because we've got x plus pi on 4, it's like when we have 2x. When we have 2x, we consider 2 revolutions. We're just changing our domain for that particular angle. Same thing here. X plus pi on 4 actually shifts our domain from 0 to 2 pi for x to pi on 4 to 9 pi on 4 for x plus pi on 4. So that's really important, and really, we've got to be really careful about that, because oftentimes I would find students not getting that solution because they haven't reconsidered their domain there. So that's really important to do.